Dhabi, and his talk is on ergodic theorems for continuous time quantum laws. Mostafa, please go ahead.
Okay, thanks very much for coming and for this opportunity to give the talk. So yeah, we'll talk about ergodic theorems in somehow a quantum setting. And yeah, I will not assume that you know anything about this, so feel free to interrupt me at any time. I don't need to finish the slide, it's okay. So what is this about? So, as you know, ergodic theory usually is an ergodic theorem is a statement that somehow a time average is equal to a space average, roughly speaking, and a bit more precisely, if you have an ergodic map on some measured space, then you have this theorem that in some convergence type, you have that the average of some observable f over a trajectory. So you start from an initial point x, and then you have your application t. So as you take powers of t, you have some trajectory, and you take the mean of f over this trajectory. And what an ergodic theorem tells you typically is that if you average f over a trajectory, uniform average, then you will get the uniform average of f over the whole space. So this somehow tells you that the trajectory covers the whole space, right? If you average any observable over a trajectory, it will be approximately the uniform average. So in some sense, this tells you that the orbit of x under t covers your space omega uniform. Because yeah, here you get, not only do you have a density everywhere, you actually have the uniform density here. So let us be a bit more specific. So well, in case of the torus, so suppose that I start from a point x0, then the ergodic, there is a classical theorem called the Kronecker-Weil lemma or theorem, whatever. Here, the geodesic flow are simply straight lines. So, and what the theorem tells you is that if you start from a point and let the geodesic flow evolve, then the orbit, you have this kind of equidistribution somehow. So this is an illustration. So you start from a point here, and you let the evolution take place. So the evolution will just be a straight line. So x0, this is your initial point, and this is the orbit plus ty0. So as you evolve, because this is a torus, sorry. So you'll go this and this and this, etc. So it's eventually you will cover the whole torus as long as you don't take a vertical direction, for example. So as long as your direction is irrational, you will cover the whole thing as in this picture. So this is illustrated by the fact that you have this ergodic theorem. So if I take any observable A, and I start from any initial point x0, and then for almost every y0, almost every direction y0, at the limit, if I average my observable over this trajectory, I will approximately get the uniform average. As you can see, it's really clear that eventually I will fill the whole torus. So these are classical theorems, and what we want to do in this talk is somehow find quantum analogs of this behavior. So this is so-called quantum ergodicity. It has a long history somehow, but I will take a different point of view in this talk. Just another extreme for illustration is if you are on the sphere. So here it's not ergodic at all. So you see, if I start from a point and I let it evolve, it will just cover a circle. So these are different trajectories. So each trajectory is simply a great circle, so it doesn't cover the sphere at all. It's very localized. So we can also ask, can we see this in the quantum level or not? So okay, so yeah, so in the classical setting, I remind you, I start from a point V. In the quantum setting, somehow I want to start from a Dirac mass at V. So typically I will work on graphs, but I can also work on the continuum. And you imagine that you start from a vertex. So you take delta V of a vertex. This will be the quantum analog somehow of starting from a point in your space. And instead of the classical trajectory, which was for example, the powers of T or the geodesic flow of as you apply it to V. Here, instead, what I want to do in this talk, I want to study the evolution of this semigroup, e power it delta delta V. So why am I doing this? Because so quantum mechanics tells you that if you start from an initial state psi, then the state of the system at time t is precisely e power it delta psi, if delta is your Hamiltonian. So this somehow tells me that what is the state of the system if I start from delta V, what is the state after some time t, if I let it evolve according to the Laplacian. And here, why am I talking about the Laplacian? Because in the geodesic flow is really the flow of a free particle, classically. So if you want it in the quantum setting, you will be talking about the flow of the Laplacian, because that's the kinetic energy. So you don't really have a potential, it's just free motion. And finally, here, instead of considering the mean of my observable over the trajectory, so remember that I was on the left-hand side, I was averaging A over a trajectory. Here, what I want to do, I will average A instead in front of this probability measure. Okay, so let's see what this means. So I start from a Dirac mass delta V. This has norm 1, right? Okay. Now this operator here is unitary. E power it delta is unitary. So the norm of this quantity is still 1. So this defines me a probability measure, let's say on my graph. Let's say that my Hilbert space is L2 of the graph. Okay? So this is still a probability measure. And what I want to study is, does this probability measure somehow equidistribute when the time grows large or not? So at time 0, it is very localized. The whole mass is at V. But what you want to do, what you want to show, if you have this kind of ergodicity, as you see, ergodicity means somehow that everything spreads out uniformly. And so you can ask, does this happen here? So if I let it evolve according to this operator, do you somehow spread out as time goes on? So this is a probability measure, right? And what I'm considering, so I will not consider it directly, I will average it first, right? So if I take, so the modulus of this square as u varies defines me a probability measure, because the norm, as I said, is 1, so the sum over u, the vertices u will be 1, and I will not consider it directly, I need to average it, okay, 1 over t, integral of 0. And technically, many people study these kind of evolutions and they call them continuous time quantum walk. So there is a different setting of discrete time quantum walk, but this kind of evolution of the Laplacian, it's known like this in the community, and there is a whole community studying these kind of things, but they typically study perhaps a bit different problems, but anyway. So so let me just repeat before. So here I will consider what I will do, okay. Before I state the theorem, is somehow what I want to do clear? So, are there any questions? Okay. Yeah. So let me state the theorem.
I have a question.
Yes.
Is this a real probability measure or a kind of complex function which integral is one?
Yeah, so it's here it's really a probability measure, positive and everything. So more precisely, what I'm studying, as you see, is the square modulus. So the square modulus is a probability measure. If you sum it over U, you will get a.
I see.
Yeah. Okay, so let's see what we'll do more precisely. So I want to say something about ZD. So my first graph will be ZD. So you can view it somehow if you want as a discretization of this torus. Okay, so the simplest one. So I will consider ZD. And in ZD, I will start with a box. So I take the set of vertices from 0 to n times D. Okay, and I consider the adjacency matrix on this box with periodic boundary conditions. Okay, so this is in dimension 2, for example. And then you periodic condition, so you can imagine that you somehow have a torus. Okay, if it's a line, it becomes a cycle somehow because of periodic condition. So you don't really see the boundary. This is, in my opinion, the most natural condition for this kind of problems. And now the theorem is the following. So I start from any point V in my cube. So, okay, lambda n. And I have the following result. I take an observable. An observable is simply a function as before. And I will average my observable in front of e power minus it a delta v, e power minus it a delta v. Okay, so why am I doing this? Because this scalar product, if you expand it, it becomes the sum of a of u. Here, a of u is just a n of u. Okay, in front of the square modulus of e power minus ita delta v of u, right? So in other words, the quantity on the left here, this mean here, is I can write it as a of u times some probability measure mu of u, where mu of u is given by this. This is, you just expand the scalar product. Is this clear? Okay. And what the theorem tells you, here I'm comparing this quantity with the uniform average of A. So the uniform average, here I have a cube with n power d points. So I'm taking the uniform average is just 1 over the size of the cube times the sum of it. So what I'm doing in the theorem, I'm comparing the average of A in front of this probability measure, which describes the evolved dynamics, and I'm comparing it to the uniform measure. And the theorem tells you that if you take a big cube, you first take the limit when the time goes to infinity. So you first let the system somehow thermalize over this cube. And then you take the size of the cube to infinity. Then in this limit, this evolved dynamics will be approximately uniform. So let me illustrate this for clarification. So remember that I start with delta v. So you imagine you have a point like this, okay, at point. And then you evolve it. Okay, so I will evolve it under e power it a. And the theorem, roughly speaking, tells you that the probability measure so that you get, so when you study the square modulus of the function that you get at each point, it will define your probability measure, and it will be very delocalized. It will be completely spread out uniformly like this.
And Mostafa, someone in the audience would like to ask a question, and that was put in the chat. So
okay,
are you encouraging the audience to ask questions at the moment, or should they wait?
If they have any question, they can just unmute themselves. Yeah. So yeah, I saw the question. What is AN? So AN, here AN is the adjacency matrix on the cube. So capital AN is the adjacency matrix. You can think of it as the discrete Laplacian. So it's simply the discrete Laplacian on the cube, and little AN is an observable. It's just a function. So I'm varying the observable. It's good to have a large class. Okay, so you vary the observables, and well, the real aim is really to compare this probability measure with the uniform measure, this one. So I'm telling you that no matter which observable you take, if you average A over this one and this one, you will get approximately the same thing. So in this sense, the two probability measures are close. Yeah. Okay, so let me continue. Yeah. So this is what the theorem tells you essentially, that you start from a point mass. It tells you that somehow it will spread out. This probability measure will be, so if, for example, here you have n square points, then on the left at each point you will have the mass at each point will be 1 over n square, because that's the uniform density. Okay. And as you can see, it doesn't matter where you start from. So I start from any delta V. I don't see it in the end. It's just the uniform average. So somehow I forget my initial state, and that's typically what happens in an ergodic setting in the classical setting. So this is used as a signature of ergodicity somehow. So that's the result on ZD, and there are many questions. But yeah, before I expand on this statement, because you can ask, of course, so what happens if I interchange the limit, etc. But before this, let me just clarify that for people who did quantum walks and so on. So in the quantum walk literature, what they usually do, they work on ZD itself, so the infinite graph directly. And in this case, intuitively, if you know that the dynamics will somehow spread out, then you imagine that this probability measure here will go to 0 on ZD, right? Because so I start from a point mass. Okay, let's say that here is a point mass, and I let it evolve. And as it spreads out, right? If you take the time to infinity, you imagine that somehow it will spread out to 0. And this is not very interesting. Okay, so the fact that mu t goes to 0 is not super interesting. So what you can do, instead, you study the process per unit time. So you take xt to have this density here, right? And you study the rescale process, so xt per unit time, and you ask, do I have now a non-trivial limit or not? So this is what people in this community call limit theorems, the limit of this process. And there are lots of people who worked on these kind of things. And for example, here is an illustration here. So if you take Z and you start from delta 0, and you take this continuous time quantum walk here, then the rescale process, so this process itself will go to 0. And we see this here because at each point I have 1 over n. So roughly speaking, you see that when n goes to infinity, you will just see nothing. Okay, but when you rescale per unit time, you will see something non-trivial, and this is the asymptotic profile for Z, and you can ask the same question R. So it seems that it wasn't known before, so we have this in the paper with Anne, we have this profile. So somehow it's the opposite of Z, which is curious. I don't really know why, but whatever. So this slide is just for specialists who work on quantum walk. I'm just saying that I'm not doing this in the present talk. Here, I'm really looking at a box of finite volume with periodic condition, and I'm taking first time to infinity and then the box to infinity. So it's not really the same as working with ZD itself. It's different. And so this result doesn't apply something on the limit theorem and vice versa. It's really a different techniques. Okay, so let me now go back to the main result. And we have some extensions somehow. So instead of, remember here I was starting from delta V. So at time 0, I'm really averaging A over delta V. And as time goes on, I'm averaging A over the square modulus of this. Some people like to ask, okay, what happens if I start from 2 different points? So here I take delta V and here I take delta W. Then if you expand the scalar product, it will no longer here be a probability measure because it will be this times this bar. Okay, so it will even be a complex measure. And what we find is that if the points are different, if you start the evolution from 2 different points, then you will get nothing in the end. So the average of A will disappear somehow. Okay. Another interesting point is that we can consider more general initial states. So instead of starting from point mass, you start from a function of compact support. And the interesting point is that let's take psi equal phi. Then the theorem tells you that if the norm of phi is 1, then you always converge to the uniform average. So this is quite interesting because if I go back to this picture, what this tells you is that, for example, suppose that instead of starting just from 1 here, I take 1 over square root of 2 here and minus 1 over square root of 2 here. So I'm allowed to change sign. I'm allowed even to multiply by a complex phase if you want. Then it doesn't matter. You will not see this in the limit. You will just go to the uniform average. So the limiting profile only depends on the norm of phi. It doesn't depend on the entries. So you can take your initial state anything you want as long as it's normalized. So, and of course has compact support. So compact support here means that the support is finite and does not depend on n. So it's just a small ball and the graph grows large. So in all these settings, it works. Now, first, so the first question you can ask, do I really need this to consider this mean here? So do I really need to average over time? And somehow, yes. So what we can show is that there is a sequence of observables such that if you consider sorry. Here I'm talking about interchange of limits because I will talk about this averaging later on. But yeah, here notice that I'm considering first the time to infinity and then n to infinity. So what happens if you consider fixed time? So you fix the time and just take the box to infinity. Will you get the uniform average? Okay, so I repeat. You have your delta V, you start from delta V and you evolve it to a finite time. Let's say up to time equal 10. Okay? You now fix the time and take the box to infinity. Will you really see a uniform density? And the answer is no. So we can find a sequence of observables such that if I fix the time, then so I just take the limit n to infinity, then the difference is big actually. So for a certain sequence of observables, this is bigger than 1/2. So it does not at all converge to the uniform average. So in other words, it's important to first thermalize, first take t to infinity, and then the box to infinity. You cannot interchange the limits. Here we state it for the evolution itself, but it's also true for the average dynamic. So also the average dynamic is also far from the uniform average in this case, if you take n first. Another thing, yeah, this is what I was telling you about that I need to consider the uniform, this mean here. So if I remove the mean, this scalar product may not converge. So there is a sequence of observables such that this doesn't have a limit. So what this tells you is that this is still an interesting question, but so we can find a sequence of times such that this quantity here goes to the uniform average, and another sequence of times such that it goes to something else. So it can still be interesting to identify what are all the possible limit points of this evolution. I think this would be pretty nice. But if you insist on having the uniform average, then you really need to take the average dynamics. Otherwise, it will not work. Okay, so that was the theorem for ZD. So in the rest, I will be talking about the theorem in more interesting settings of periodic graphs where you have more interesting profile. But are there any questions up to this point? Don't hesitate to ask. I mean. Okay, if not, then let's see what happens if instead of ZD, I take other graphs. So somehow the periodic graphs. So the theorem itself gets a bit technical. So I will tell you in words what happens, and then give you some examples where you can see. So what happens is, so first of all, what's a periodic graph? What do I mean by a periodic graph? I mean ZD periodic. So you imagine the honeycomb lattice, you imagine triangular lattice, whatever, you imagine an infinite ladder, a strip. So the only condition you have is that you have some kind of fundamental domain, and you copy it over the action of ZD. So for example, if I have a Z periodic graph, it means that I have some kind of finite graph, and I'm periodizing it over the line. Okay, it can be very general. And the spectral theory of this graph is very beautiful. But because it's so general, things can get a bit messy, and you can find somehow counterexamples to this kind of ergodicity. So you need some conditions. And so if I want to be very non-technical, I will tell you that the theorem remains true if this periodic graph only has absolutely continuous spectrum. So if I just have purely absolutely continuous spectrum, somehow the theorem is true. But this is not completely correct. Okay, so I need something stronger than absolute continuity of the spectrum. I need my these periodic operators. They are analyzed using Floquet theory, and I need my Floquet matrix to have somehow well-behaved band functions. So very, very roughly speaking, what I need is that, so if you are familiar with Floquet theory, I have a problem when there is some kind of degeneracy. So not exactly. So if I have two band functions which are identical at all quasi-momenta, there is no problem. Okay, I can handle this. This is not a problem if the two band functions are identical. However, if two band functions at times, so at zero, are far apart, and then is there a question?
No, todo bien, profesor.
Okay. So
Thanks.
yeah. Okay. So let me repeat. So if I have two distinct band functions, so at some point they are distinct, and then they start touching each other, and then they leave, and then they start touching each other, and so on. If they touch each other too much, so on a set of positive measures, then I have a problem. Okay? So I don't want this kind of behavior. So roughly speaking, if you have this, then you have this kind of ergodicity. And what's important now is that you will no longer get the uniform average. So you will get something absolutely, somehow absolutely continuous profile with respect to the uniform density. And we will explore this in a moment. So if you are not familiar with Floquet theory, you can completely forget this. It doesn't matter. But for specialists, I need some kind of control. And in particular, this kind of control is true if you consider periodic Schrödinger operator on ZD. So suppose that I start from ZD, but now I add a periodic potential. And instead of considering the evolution of the adjacency matrix, I consider the evolution of the periodic Schrödinger operator. Then this kind of theorem is still true, as I will show you. Here you will not get the uniform density, you will get an absolutely continuous density, but you still spread out somehow. Okay? And the fact that this condition on the band functions is true for this kind of operator was shown by Wen-Tsai Liu, who will be talking tomorrow in the conference. So using his result, I can apply his result to deduce that I have this kind of ergodicity. Okay, so let me now give you more examples so that you don't get lost. So here is a very simple periodic graph. I have this ladder. So it's just an infinite ladder, and I truncate it. So I truncate it to have from 0 to n. So I have 2n vertices. So I have like this, and then I take periodic conditions. So essentially it means that I take it on a torus like this. Okay, so that I don't have a boundary. I consider the adjacency matrix of this graph. So I start from a point mass. This is my delta V, and I evolve the dynamics. So remember that in case of ZD, you had uniform distribution as a limiting profile, and this is still true here. Okay, So we can apply our result for periodic graph to see that if I start from a point mass here, then eventually it will spread out uniformly. In other words, at each gray vertex here, I have mass 1 over 2n. Okay, so it's really equal weights everywhere. That's this probability density here. This square modulus here will be uniform everywhere. Good. What if I change my graph? So what if I take now a 3 strip? So a strip of size 3. Then curiously, this will no longer be true. So suppose that I start from a point mass here. Then asymptotically, it is true that I will spread out, but not uniformly. So eventually, I will have more mass on this layer and the bottom layer than in the middle. And we can calculate exactly what mass. So here I will have 3 over 8 of the mass will be here, 3 over 8 of the mass will be here, and 1 over 4 will be here. So there is more mass here and here than. Okay. And by 3 over 8, I mean that if this is 1, then at each red vertex, you will have 3 over 8n. Okay, so that the whole sum in the end is 1. Okay, so essentially there is more mass here and here. And if you start from the middle, so if you start from a point mass here, it will still not spread out uniformly. So you will have eventually you will have more mass here than in the here. Okay, so it's still somehow it's still spread out. So if you take the size n to infinity, somehow at the end you will not see anything, right? It will all weights are of order 1 over n anyway. So you will everything goes to 0, but it's not uniform. And here, when I saw this, I said maybe it's because of the degree. So here you have degree 3 and here you have degree 4. So these 2 points are not completely equivalent. So maybe that's the reason why you have this kind of behavior, but that's not the case actually. So even if you take a cylinder like this, so this is just Z periodic, right? Like this one, these are all Z periodic. So in both this graph and this graph, the dimension is just 1. So now you have a regular graph, all points are the same. So I take, I start from here and I evolve the dynamics. And curiously, this is still not uniform. So asymptotically, you will find a limiting profile like this. So you have more mass here and here than in these 2 layers. So I don't really know why this happens. I get these things by computation. So and it seems to me that this is a quantum effect. So if you consider a classical random walk, I think that the limiting profile will be actually uniform. So this seems to be a quantum effect. If you have an explanation for this, please tell me, but I don't really know. By contrast, to suppose that instead of a point mass, I start from a uniform density over this square. So this square here is my fundamental domain. As you can see, this is what I keep repeating. If you start from a uniform density here, you will get a uniform profile in the end. Okay, so if you evolve this initial state, everything will become uniform. But even that is not true in the previous graph. So if I start here from a uniform density over the 3 vertices here and I let it evolve, the limit will still not be uniform actually. So starting from a uniform density over the fundamental cell is still not enough in general. Sometimes it works and sometimes not. And anyway, so as you can see in periodic graphs, so when we leave ZD, the limiting profile does depend on the initial state. But it depends in a limited way. So it doesn't depend where you start. So let's say in this graph, it doesn't depend where you start horizontally. It only matters where you start vertically. So more precisely, it only matters where you start in a layer of the fundamental domain. So if I translate this layer, it doesn't matter. You don't. But inside the fundamental domain, you may see differences depending on where you start. Yeah, and just a word of caution. So as I told you, because periodic graphs are so general, sometimes they actually have localization. So you will not find this kind of behavior at all. Okay. So this is an example. You consider this very simple graph. and you start from your initial state is 1 over square root of 2 in this vertex, minus 1 over square root of 2 here, and the rest is 0. So you start from an initial state localized in 2 vertices, and you let time evolve. And what will happen actually is that your state will stay frozen on these 2 vertices all the time. So it's not at all ergodic. It's very, very localized. So you start from a localized state, it stays frozen at all times under the evolution. And why does this happen? This happens because this graph has what people call a flat band. So it's an infinitely degenerate eigenvalue. This you don't see in ZD, you don't see in ZD with a periodic potential. This is quite specific to when you leave this classical framework and start investigating these crystals. And you can see that this is already a counterexample, so you need at least to avoid these flat bands. So remember when I was telling you that I need my spectrum to be absolutely continuous, you can see that this is really needed. But yeah, as I was saying, I need a bit more than absolute continuity. I need some kind of control on the band functions. Okay, so these are the theorems for the discrete setting. Are there any questions before I move to the continuum? Any questions? Okay, let's see what happens in the continuum. So now I will work on the torus itself. So it's really the continuous torus. It's no longer a graph. And I want to do the same thing. But the problem now is that when I consider delta y, so I want to start from a Dirac point, Dirac mass at a point. But the problem now is that this is a singular quantity. So it's not like a graph where I can just define it to take value 1 at the vertex v and 0 everywhere else. Here, the Dirac mass is a singular quantity. So this is bad because I wanted to start from a probability density. Remember that here, in my analogy here, I wanted to start from a probability measure so that this remains a probability measure. I mean, the square modulus defines a probability density. So that's why I need to start from an L2 function. And what I will do is that I will first regularize it. Okay, so I will regularize this Dirac mass, and you can regularize it in different ways. So you can regularize it in momentum space. So you start from your Dirac mass, and you apply the spectral projection of the Laplacian to this. So you can make sense of this, okay, even though this is a distribution. And you properly normalize it so that this quantity here now has norm 1. And what happens when you do this, this is actually a trigonometric polynomial. So it's a very irregular quantity. That's a possible way to regularize your Dirac point. Another way is to simply take characteristic function of cubes, which are smaller and smaller and properly normalized, right? So you imagine you start from a point y, okay, and you take a small characteristic function of a small cube of size epsilon near y, and you take the size of the cube to go to 0. And because you are normalizing it, this becomes a peak, so somehow you go to the Dirac distribution in the end. So these are two ways. This one is trigonometric, it's smooth. This one is not smooth, but whatever. It will not matter in the end. But somehow this one actually becomes more difficult in the analysis, but it still works. Okay, so let's see what we have. So I will try to do exactly the same. So I start from a point y in the torus. I have my observable now. I take it to be a Sobolev function. So this function here is just Sobolev. And I do exactly the same. So I compare the average of A over this probability density, and I see what happens in the end. And curiously here, you don't need to take time to infinity. You do not need the system to thermalize. So you just, in the limit E goes to infinity, this means that your approximate Dirac point becomes more and more singular and approaches the point measure, approaches the Dirac measure. So this parameter E here is just the approximation that you have of the Dirac point. And what this tells you is that if you just take a positive time and you consider this, then as E goes to infinity, as you approach the Dirac point at Y, you will find the uniform average of it. So you don't need to consider big times. This already, at any positive times, it already is thermalized completely. Okay, so somehow you can think that I have somehow an infinite speed of propagation somehow. So I mean, very naively, if I make an illustration, so I start from something that is close to a point mass, and as soon as I get T bigger than 0, everything becomes completely uniformly spread out. It's a bit curious. But people in semi-classical analysis told me that one way to explain why this happens is that here I'm considering e power it delta. In semi-classical analysis, they would consider, I think, e power it h bar delta, where h bar is the Planck constant. And the fact that I'm taking the Planck constant to be 1 in their language somehow means that I'm considering big times already. So in their language, h bar is typically something that is very small. And here I'm taking it of order 1. So that's one explanation why things somehow thermalize automatically like this. So anyway, so you have this. So I repeat, so it's very close here because we are talking about the continuous torus, so we can really compare it with the initial Kronecker-Weil lemma. Remember this one? So it's really the same type of statement. Now I'm really on the continuous torus itself, and instead of starting from a point x0 in the torus and evolving the dynamics and considering A over the trajectory, and in the end getting this uniform average, I'm doing exactly the same here. Sorry. But I'm now averaging A over the probability, I'm averaging A over a certain probability density on the torus. And when my initial state gets close enough to a point, I get the uniform average of it. So this probability density is really the uniform density. If you take a Dirac point, somehow you get the uniform density of the torus. And then you can do exactly like we did in the discrete setting. So again, if you start from 2 different points, you will get nothing in the end. So here I remind you, I'm averaging A over something which is not even a probability measure. Sorry.
May I ask a question?
Yeah, go ahead.
What maybe it's a stupid question, but what if instead of using e to the it delta, you use e to the t delta?
T delta, then in this case, it's no longer unitary. I mean, this is the heat kernel, right? So
yeah, but there is some kind of preservation because if it is periodic, you don't lose mass or something.
No, but I mean, the norm will not be 1.
The norm will not be 1, yeah. So
yeah.
Yeah,
okay. I don't know. Yeah, you can definitely ask what will be the limiting profile, but I have not tried to consider this. So I don't know how if you start from a Dirac mass and then you evolve it under the heat kernel, what will be the limiting profile? I have no idea. Maybe you can properly normalize things. This is a good question. I don't know.
And you may get the e to the it delta as a kind of analytic continuation of the e to the t delta, maybe.
Yeah, I don't know.
Yeah, okay.
Thanks for the question. Another point, this is more again for specialists, is that I can, instead of taking just an observable E, I can take this observable to depend on this parameter E. So this gives you a bit finer theorem in the sense that you can take the support of your observable to shrink with the energy. So it gives you a bit finer detail that you have this equidistribution in a finer sense. Not only is it true if I have a fixed observable, it's still true if the support of the observable shrinks. So it's somehow a finer detail. The same proof actually works in this. So some people are interested in this. And here I can state the theorem a bit more precisely. I mean, because we are in the torus, so you know, in the discrete setting, what's annoying is that at each n, you have a different space. So that's why I had a sequence of observable an. Here I just have one observable, so it's a lot easier. So I can formulate it in terms of weak convergence of measures. There is a question in the chat. So there is a comment about this heat semigroup. Yeah, maybe the person who asked a question, maybe I think this can be interesting. Yeah. Okay, so yeah, so I was saying you can now, for the case of the torus, you can formulate it in terms of the limit, weak convergence of limits. So if I start, remember I start essentially from delta y, which is some kind of localized thing. And I consider this probability density and I average it. And what you can deduce from our theorem is that this thing here will converge weakly to the uniform measure dx. This, you can extract it from this kind of thing. And this happens, so this converges to the uniform density as e goes to infinity. So it doesn't matter where you start from, y doesn't matter, your initial point doesn't matter, and time itself doesn't matter. You just need to take a positive time. Okay, in the end, you will always end up with the uniform measure. Okay, so very roughly, again, we have this. Okay. And you have exactly the same kind of comment. So time averaging is again necessary. So this may not have a limit. And remember, so this delta ye was a regularized delta function in momentum space, but I can also regularize in position space. So I just take characteristic function of cubes and the theorem will still work. So this is the other theorem here. So suppose that I start from characteristic function of cubes like this, or rectangular box if you want. And I average e power it delta in front of this characteristic function, and I take the size of the box to go to 0. Okay, so I get closer and closer to a Dirac mass at y. Then again, you have exactly the same. So it doesn't matter if your initial state, how you regularize it, you will still get the uniform average in the end. And similarly, if you start from two different points, you get nothing in the end. This is in terms of weak convergence. So this measure here converges to the uniform measure. So these are the theorems on the torus. Any question? Okay, so the last theorem was the sphere. So remember that on the sphere, I do not expect to have this kind of ergodicity because here the geodesic flow is not ergodic at all. It's completely localized somehow on great circles. And you have somehow an analog of this in the quantum world, but it's not as sharp as this. So what I can tell you is the following. If I start from a delta sequence, so something which is essentially a regularized delta function, and I let it evolve, so this delta sequence, in the end, it will not be equidistributed on the sphere. So what I can definitely tell you is that if you consider this kind of limit, you will not get the uniform average here. You will get something else. What do you get is more subtle. Okay, so this I cannot really tell you, I think. And in dimension 3, so you can make calculations, and I can give you an explicit observable such that the mean of this is not really the average. Okay, so essentially what I want to say is that on the sphere, this result is not true. You do not equidistribute. And curiously, so I talked because so there is a mathematician called Fabricio Macia, so he's in Spain, I think, and he studied these kind of evolutions a lot on the sphere, and he told me, if I understand correctly, is that actually what he expects will happen, and I think it's even somehow contained in one of his papers, is that eventually you will actually get something which is absolutely continuous. So it will not be singular like this, because you could expect that in the quantum world, somehow my limit is something singular. So it's, I don't know, a measure which is concentrated on a circle, something like this. So it's singular with respect to Lebesgue, but that's not the case actually. What you will get is something absolutely continuous with respect to Lebesgue, but it's not uniform. So we show in our theorem it's not uniform. And but somehow it does, yeah, so it will get, yeah, if I understand correctly, you will get some kind of divergence at the poles. So you will get singularities, but still in L1 sense. So anyways, this is the case of the sphere. And these were all our theorems. So yeah, so this is exactly what I was telling. So let me just give you some earlier literature before I move to the proofs, if I have some time. So this is not the first time that people have tried to study a quantum analog of ergodicity. So what people have been doing a lot is studying quantum ergodicity in terms of eigenvectors. So what I did in this talk is that I started from a point mass, delta V, and I consider its evolution. Okay. What people have been doing instead is you consider, let's say, let's go back to the torus, for example. So what you do here, to compare the geodesic flow, you look at the Laplacian on the torus, that's the quantum world, and you consider just the eigenfunctions of the Laplace operator. And what you show is that most eigenfunction in the high energy limit will somehow equidistribute. So it's not exactly the same question. You don't start from a point and let it evolve. Instead, you just look at the eigenfunction and see if they equidistribute on the torus or not, as probability density, because you take your eigenfunction to be an orthonormal basis. So again, you get probability densities, and you can ask if these probability densities defined by the eigenfunction somehow get uniform or not. And the answer sometimes is yes, sometimes no. So for example, in the torus, yes, it happens, and so on. So there is this kind of approach of quantum ergodicity in terms of eigenvector has been studied a lot. There is some physics heuristics which tells you that if you have quantum ergodicity for eigenvectors, you can deduce it for the dynamics, which is what I want. But unfortunately, it doesn't really work. So if I have time, I can talk a bit about this. So what we do, we in our paper, we don't use quantum ergodicity of eigenvectors at all. We really prove everything from scratch. If you really want to make sense of this physics heuristics, it will be more difficult to justify, and actually you can find counterexamples somehow to what they say. So it's still a good heuristic somehow. And it can work in very specific setting. I think it can work in random matrices, for example, but in this case, in this setting of deterministic setting, I don't think it can work. Another point, yeah, so there are many works on the dynamics in the continuum setting. So I told you we have some results on the torus, and people have been studying this kind of dynamics, not really from the same point of view. So they don't really consider Dirac point and try to see how they evolve. Instead, they consider what they call Wigner measure. So I discovered this after I finished the paper with Anne. And essentially, you can extract a lot of results from these papers. So this is a paper of Fabricio Macia with Nalini Arantaraman here and Gabriel Rivière. So there are much more works in the continuum, and they don't necessarily give you something precise like this. So you don't really get the uniform density, but I think you can extract from this paper that you will get something absolutely continuous. And this is not trivial, so we will not really find a statement like this in these papers, but you can somehow, if you know some micro-local analysis, you can get this kind of results from these papers. In our case, the proof is really simple, so we do not need micro-local analysis. We really do everything by hand. It's an explicit computation, and it just works. So, and the proof is pretty short. So these are the works in the continuum. There are some earlier works, but in case of graphs, everything is new. So many people have studied discrete graphs, but this kind of ergodicity is really new. So that was the earlier literature and some immediate open problems. So yeah, so okay, this question here will is what is the limiting profile in for certain specific graph? So here I computed to you the asymptotic density for this specific graph. For this specific graph, I computed the asymptotic density, and you can ask, can you give more examples? So in general, I have a formula for the asymptotic density, and it would be interesting to compute this formula a bit more precise for more families of graphs and try to understand why this kind of behavior happens. Another question is to consider discrete, what people call discrete time quantum walks. So these are no longer evolutions of the Laplacian. They are instead unitary operators, which are defined by coins and so on. And you can ask exactly the same question. So if you start from a Dirac point, a Dirac measure at a point, do you somehow eventually get something uniform or not? So this, I think, would be pretty interesting. And yeah, this is a remark. Yeah, so this is a remark about the fact that this quantity here, remember that I'm essentially considering this and seeing how it behaves when times grow large and then the graph grows large. So the fact that this quantity, this average dynamic converges when the time grows large is quite trivial. So this is what I need, for example, in graphs. The convergence itself is trivial. What's non-trivial is showing that the limit is uniform. And why is it trivial? Because if you just consider the spectral expansion of this, so if I expand e power ith in terms of orthogonal projections, and I consider the square modulus, then if you expand the square modulus, you will get cross term, so you will get a sum over k, a sum over r, let's say, and here you will get e power it ek minus er. So if these all the eigenvalues, so here these are spectral projections for distinct eigenvalues. So if you average, you will get something. So all these cross terms will vanish, and you will just get this in the end. Okay. So the fact that this here converges is easy. It's just very simple. But what's not trivial is proving that this thing here is actually a uniform. It doesn't really depend on x. It's just 1 over n. And actually, so this long-term dynamics, we don't use this in our paper. We don't consider spectral projection because they are quite complicated. Remember that in case of ZD, for example, the multiplicity is very large. The multiplicity, let's say, of eigenvalue 0, it grows with the size of the graph. So this is it's not an easy operator. So we don't pass by these things in our proof, but this is just to tell you that convergence itself is not a problem. The problem is studying the limit. Is it uniform or not? In case of long-time dynamics. In case of the torus, as I tell you, we don't even take a long-time dynamics, so this is completely useless. Okay. And yeah, this was the heuristic, so maybe I can conclude with this. I will not have time to talk about the proof. But I can conclude, so this is the physics heuristics I was telling you about, that maybe one can pass from quantum ergodicity of eigenfunctions to the dynamics. So the physics heuristic is the following. So I will start from from an initial state phi, and I consider the average of A over this. So this is what I want to study. And I assume that I know that I have a quantum ergodic basis, so I know that I have some kind of privileged basis of eigenvectors, such that this eigenvector psi m somehow become equidistributed. So what I will do, I will simply expand this over this basis of eigenvector. So this gives me this quantity here. I've simply expanded e power ita phi over the basis of eigenvectors, and I do the same in the right. Okay. And I expand this scalar product. So for m equal to n, this will give me this. Okay. And then I have cross term like this. Okay, so you just expand this thing. Now, okay. So now what you want to argue is that if you take 1 over t, the integral from 0 to t, you want to say that all these cross terms don't matter. Okay, so somehow they vanish asymptotically. And you want to say that this is essentially, this quantity here is essentially 1. So let's go over each thing. So if I take the integral 1 over t, so 1 over t, the integral from 0 to t, why would this go to 0? This error term? This would happen if the eigenvalues are all distinct. So if lambda n is not equal to lambda n whenever n is different than m, then indeed you can integrate this. It will give you an error term as 1 over t, essentially, and over 1 over capital T, and this indeed will go to 0 if the eigenvalues are distinct. But if the eigenvalues are the same, so if you have degeneracies, then the problem is that this will just be 1. And if you integrate 1 over t, the integral from 0 to t, you will just get 1. So this error term will not vanish. So you can see that if you have degeneracies, already this is a problem. And the other problem is that here you would, I mean, the physics argument is that this is essentially 1, the uniform average, because this eigenbasis is essentially uniform. So when I average it here, I get essentially the uniform average. But this is stronger than quantum ergodicity. This would be something like quantum unique ergodicity, which is not true in all these examples that I talked about. So actually, this kind of argument is not true. You can actually find counterexample for some specific states, phi. We give them in the paper. So, but maybe this can be useful in other settings, not in ours. Okay, I think my time is up, so I can finish now. And yeah, if there are any questions, please go ahead.
Yes, thank you, Mostafa. Are there any other questions or comments for Mostafa?
Well, I have a question. You mentioned that, well, if you add the potential and the periodic potential and the spectrum is absolutely continuous, then maybe a little bit more, then ergodicity remains.
Yeah.
But I was wondering if in your setup, there are cases when you add a potential that would destroy the ergodicity. So with potential 0, suppose it's ergodic, is it done if there are potential that could eventually destroy this ergodicity?
Yeah, so I mean, the spirit here is that as long what I mean, ideally what we want is that as long as you have absolutely continuous spectrum, you have this kind of ergodicity. So that would be the dream. So definitely, if you add a potential that gives you point spectrum, then you have trouble. Okay, so you will have a frozen part in your graph, and I mean, if you evolve just an eigenvector, it will just stay frozen everywhere at all times. So you can ask what happens if I add some kind of potential that preserves the absolutely continuous spectrum. So I still am absolutely continuous. Do I still get ergodicity? That would be the dream, but so far we only have it in quite specific situations. So here I really need it to be completely periodic. In a previous work with Nalini, I worked on the Anderson model, but it was in the setting of graphs which converge to trees. So it's quite specific. We cannot, I mean, we cannot consider arbitrary potentials now.
Okay, so and no examples are known, no counter examples are known. Of course, if they don't add bounded states.
So if you have absolutely continuous spectrum and you don't have ergodicity, actually we have some kind of counterexample in my paper. So in an earlier paper with Theo Mackenzie. So in this setting of graphs. So remember that I said I need something more than
Yes.
than absolute continuity. We have an explicit graph I can show you. It's a pretty nasty graph, but on which you can show that the spectrum is absolutely continuous, but you don't have this ergodicity. So you need something more than absolute continuity in general. And here in case of periodic graph, we can show this.
But what you need more is some regularity of this.
Not really
Not-
regularity. So in terms of band function, it was this kind of behavior that I don't want the band function to keep hitting each other in the dispersion relation. So yeah, in general, it seems, I mean, even in case of trees, it was a control over the Green's function, for example, if this is more familiar. So yeah, it seems you need a bit more than absolute continuity in general. But there are very few general statements.
Okay, well, thank you.
And Delio, please go ahead.
Thank you, Mostafa, for a very nice talk.
Thank you.
In some sense, my question is orthogonal to that of Ricardo. So what if you do not perturb the diagonal, but the off-diagonal entries of your matrix? So, I mean, so it was not completely clear to me to which extent you use the fact that you have a Laplacian of a graph. So could you, for instance, flip the sign of some off-diagonal terms, or have some kind of local perturbation of your graph, or have some kind of sign graph, something like this?
I don't know. Yeah.
I mean, I'm thinking of something like square root of a Laplace, or maybe the B Laplacian, which certainly will have some negative of diagonal entries.
Yeah, I never thought about this. Yeah, so I only worked with just Laplacian Schrödinger operators, but if you start instead doing this, I don't know. I can't say for sure. Yeah, I need to look more closely. I mean, working on ZD with just the Laplacian here is the proof for the Laplacian on ZD is quite simple, and maybe you can start to work in this setting and seeing for the simplest case of what you're talking about, the simplest operator. Maybe we can examine that. Yeah, I don't know I haven't tried it.
Okay, thank you.
Are there any other questions? No. Well, if they're not, Ricardo, I assume that you will close.
Okay,
Very
well, we thank the speaker then for this beautiful and very interesting talk. And
Thanks
then,
very much.
and if there are no further comments, then I would close the session. Okay, so see you tomorrow at 9. Bye-bye.
Thank you.